Hi everyone, this is Dr. C. Manjuna. I'm an associate professor in the Department of Chemistry, RV College of Engineering, Bangalore. So in this video, I'll be discussing about the fourth part of the computational chemistry. This is there in the course called Chemistry of Smart Materials and Devices, which is introduced for the first semester computer science and allied branches. So in my previous recording in the part one, I have discussed about the introduction to molecular modeling, scope, cost, efficiency, excuse me, and computational modeling, and have discussed about covalent and non-covalent interaction. That was in part one. And in the part two, I have discussed about molecular topology, and in that I have discussed about topological matrix like vertex adjacency matrix, edge adjacency matrix, and distance matrix. And the third part, I have discussed in detail about topological indices like Zagreb number, Wiener number, and platinum. So in the last part in this video, that is in the part number 4, I'll be covering the prediction of molecular properties through QSPR, QSAR, and structure property relationships, QSPR and QSAR. So let me discuss QSAR and QSPR in detail. So what is meant by QSPR? QSPR is a quantitative structure property relationship. It is a method that correlates the molecular structure with physicochemical or material properties. So typically, the properties that we are predicted using QSPR model is the boiling point, the melting point, solubility, viscosity, and partition coefficient, conductivity. So these are the physicochemical properties are being predicted for the given material. But in QSAR, it is the quantitative structure activity relationship. This correlates the molecular structure with biological activity. So that whatever the drug selectivity and the toxicity. So that can be understood by using this QSAR model. So this is example of activity like drug potency, enzyme inhibition, toxicity, and pharmacological responses. So overall, if you compare the QSAR and QSPR, QSPR is actually physical material property. QSAR is biological property. The application of that QSPR model is that to understand the properties of the materials, polymers, and solvents. However, QSAR is exclusively for biotechnology and drug discovery and pharma industry toxicology. So in QSPR, we use topological indices, electronic configurations, geometric configurations of the material in order to predict the physical properties. In QSAR, along with this topological, electronic, geometric, we also study the biological, use them to understand their biological activity. Models are regression or machine learning in both the cases. The core principle is in QSPR is the structure and property, and QSAR the core principle is structure and activity. So this is the step-by-step flow chart that is followed in modeling or predicting the property and activity of the material in QSPR and QSAR. So the first step is the selection of the compounds or data sets, and second step is the molecular structure preparation. So then the molecular structure to graph, network graph, and graph to matrix representation. So then the third step is the descriptor calculation. And then the fourth stage is the descriptor selection. Descriptor is whatever that Zagreb topological indices, Zagreb number, Wiener number, plot number. So the fourth step is a descriptor selection, where it involves the correlation analysis. Then the fifth step involves the removal of redundant descriptors. Then the sixth one is the model building or curve fitting. The seventh stage is the model validation. Then once the model is validated, we get the activity of the material or the physical property of the material is being predicted. So that is N. So these are the various stages which are involved in QSAR and QSPR studies. Let us understand QSPR, the structure and property in detail. The objective of QSPR is to predict, for example, let me take this substituted benzene as an example. Let us understand how QSPR and QSAR is applied for substituted benzenes. The objective is to predict the boiling point of substituted benzene. How does the molecular structure of this substituted benzene influence the boiling point? Okay. So for this, the descriptors used are the molecular weight of substituted benzene. So that is also some number. Then Wiener index, Zagreb index, and also the dipole moment. So all these parameters or the values are being are considered as an input. So then the QSPR model, the property is the boiling point is equal to C0 plus, these are the regression coefficients, C0 plus C1 into the molecular weight, the first descriptor, C2 into Wiener index, C3 into dipole moment. So this is the formula used, and these are the descriptors. The outcome is, this is the input, okay, for that model. The outcome is it predicts the boiling point of new substituted benzene. So no experiment is required. So this can, the boiling point of the substituted benzene can be studied, understood by using this QSPR model. So it's used for solvent selection, process design, and materials screening. Next, let us understand the QSAR of the same molecule, substituted benzene, structure activity. The objective is to predict antibacterial activity of substituted benzenes. The question, the QSAR question is that how does the molecular structure influence the biological activity? In case of QSPR, how does the molecular structure influence the boiling point? This is a physical property, right? So the descriptors used for the QSAR is the hydrophobicity. So hydrophobicity and hydrophilicity, which influence the activity of the material, it is represented by log P. And electronic parameter like Hammett constant, topological indices like Zagreb, Wiener, and plot number. Then steric descriptors. Of course, we have not studied all the descriptors, but we have to give most of the descriptors as inputs in order to understand the activity. So more the input, better is the result. The QSAR model, the formula is the biological activity is equal to C0 plus C1 into log P. This represents the hydrophobicity of the material. Then C2 into sigma, this is Hammett constant, which represents the electronic parameter. Then the Wiener index W, and C3 into Wiener. So the outcome is to, this predicts the drug potency or the toxicity. So identify promising drug candidates. So this QSAR, it's used in drug discovery, toxicity prediction, and environmental risk assessment. So this is how the QSAR and QSPR are used for a given material. So in detail, the quantitative structure-property relationship is that it predicts the physicochemical properties. Based on the principle, the structure is converted to descriptor and then descriptors to property. So this we have discussed in detail. So the first step in QSPR is that selection of the compounds is the first step. So choose the compounds with known experimental properties. Okay. So the data set should be large and chemically diverse. So the rule of thumb is at least greater than 10 compounds per fitted parameters. The significance of this stage, the first stage in QSPR, is that it ensures the statistical reliability and avoids misleading correlations. Then the second stage in QSPR is that the predicting the molecular structure. So once we select the compounds, then molecular structure, that is also then topology. So we have to generate the molecular structure using theoretically optimized geometries and crystal structures if available. So for simple QSPR, the connectivity topology may be sufficient. The significance of this stage is that it provides the uniform structural input, right? And it also enables the prediction of unsynthesized molecules. So this is the second stage of QSPR. The third stage is the descriptor calculation. So descriptor calculation. So at this stage, it converts the structures into numerical descriptors. So this we have discussed in our previous recording. Structure, the molecular structure is converted to graph, and graph to matrix, and matrix to topological indices. So here the molecular weight, it's a given, it will be some number. And topological indices like Wiener, Jogrib, and plot that we have discussed in our previous recording. Then energies, charge, vibrational data, all those data are represented as some descriptors at this stage. So these are all obtained from molecular mechanics and semi-empirical methods. The significance of this is that it translates the chemical structures into mathematical numbers, so like quantitative data. Then the fourth stage is that once you calculate the descriptor, you have to select the proper descriptor. So that is for correlation analysis. Calculate the correlation between the descriptor and property. Okay. So select the descriptor with high correlation coefficient. So high correlation coefficient. Describe the descriptors with poor correlation coefficients at this stage. So the significance of this stage is that it identifies the structure sensitive parameters, improves the prediction accuracy. Then the fifth stage of QSPR is that removal of redundant descriptors. Compute inter correlation between the descriptors. If two descriptors give similar information, so retain the more relevant one and the other one remove that. So avoid using the redundant descriptors because it prevents overfitting and improves the model stability. So this stage. Then the next stage is that the model building. So once you remove the redundant descriptors, next you have to go for model building, that is also called curve fitting. So for that, to fit a mathematical relationship, property like boiling point or melting point or any other the dipole moment, the physical properties, right? So property is equal to C0 plus C1 into D1 plus C2 into D plus SR. D1, D2 are the descriptors, and C1, C2 are the coefficients. The common methods used to build a model or curve fitting is that linear regression or matrix least square. So nonlinear terms used only if justified. Significance that it establishes the structure property relationship. So D1 and C1, C2 are regression coefficients. So it is actually the numerical weights assigned to each the descriptor, the percentage of the contribution of each descriptor. So in that equation that C0, C1, CD, the C terms, this one, the C0 is actually intercept. It is the constant term. The value of C0 of the property, when all the descriptors are zero, it actually represents the baseline contribution. So physically, intrinsic property not explained by chosen descriptors. So that is the meaning of C0. C1 and C2, they are called regression coefficients, are also called weightages. It quantifies how strongly each descriptor affects the property. It's determined by curve fitting or regression from experimental or computed data. The positives, if the C1 and C2 are positive, it means that property increases with descriptor with DI. If it is negative, if the CI is negative, the property decreases with the DI. So therefore, large the magnitude of CI, a strong influence of that descriptors. So that is the meaning. Okay. So then the D1 and D2 are descriptors. They are also independent variables. For example, the grain size, the band gap, the particle size. In simple words, Okay. D, if for a UG student, you can understand only to this extent. DI is what you measure or calculate. CI is how important that parameter is. So curve fitting finds the best value of C0, C1, C2. So the equation matches the real data. For example, for research level, for a material science level, if you want to understand this helps to establish structure property relationship, identifies key controlling parameters. So that is about then the next stage is the predictive equation. So the final QSPR equation obtained, it contains the selected descriptors and optimized coefficient like so D1, D2, D1, D2, etc. This is C1, C2, etc. So the significance is that it converts the data into useful predictive tool. So then the final is the property prediction from that predictive equation. Apply QSPR equation to new molecules and hypothetical compounds. So no experimental measurements are required. Okay. So it saves time, cost, resources. It enables virtual screening. So the overall final summary is that that QSPR links the molecular structure and property. So it uses descriptor and statistical and ML tools. Helps in rational material design, reducing experimental effort. So similarly, let us understand the QSAR, the quantitative structure activity relationship. It predicts the biological activity from a molecular structure. Again, it is also same, the structure, descriptor, and activity. Instead of property, we will be having activity. It's widely used in drug design, toxicology, and environmental chemistry. The first stage is similar to that, selection of the compounds. Okay, choose compounds with known biological activity. This is called lead compounds. The data set is usually small, at least 3 to 5 compounds per descriptor. Then the second stage is the molecular structure and topology. Generate the molecular structure using optimized theoretical geometries, the molecular connectivity of a simple QSAR. Use consistent computational method for all the molecules. That is a second stage, similar to that QSPR. Then the descriptor calculation. Convert structures into numerical descriptors. Here, the numerical descriptors are different. Okay, because we are going to measure the activity. So therefore, here the descriptors like hydrophobic property, log P, electronic charges like Hammett constant, steric or size or shape effect. Then, of course, we also use the topological indices, Wiener, Jogreb, and plot number. So then the descriptors calculation, after that, we have a descriptor selection. Calculate the descriptor relation between the descriptor and biological activity. Select the descriptors as I explained in my previous, while explaining about QSPR. Select the descriptors with strong correlation and discard the irrelevant descriptors. Once the descriptors are selected, then we have to go for removal of redundant descriptors. So compute correlation among descriptors. If two descriptors are convey similar information, retain only one and avoid collinearity. Then the model building. So here fit a mathematical relationship with respect to activity is equal to C0, C1 plus C1 into descriptor 1 plus C2 into D2, descriptor 2 plus etc. So by using the linear regression or matrix least square method. So then we have a predictive equation. The final QSAR equation is obtained. So it relates selected descriptors to biological activity. It enables the computational screening, guides the molecular modulation. Then the final is the activity prediction. Apply that QSAR model to new molecule and hypothetical drug candidates. So to predict the potency, toxicity, and pharmacological response. So this will reduces the experimental cost and accelerates drug discovery. So this is about the quantitative structure activity relationship. So these are the advantages: saves time, reduces animal testing, enable virtual screening, no need of receptor structure. Limitations are valid only within the trained data set, does not distinguish binding or transport effects. Correlation does not imply, okay, causation. The final summary is that this quantitative structure activity links the molecular structure and biological activity. It uses the molecular descriptor and statistical and ML tools. It enables, it's very essential tool to for the discovery of the new drugs, toxicology, and also the assess environmental toxicity. So overall, the QSAR enables the rational design and screening of biologically active molecules, usually in silico methods. So this is about QSAR and QSPR. Let us understand by taking one example. You can see that these are the various stages of QSAR. QSAR. The first is molecular structures, descriptors, data pre-screening, multivariate analysis, statistical evaluation, and then the model. Okay, the fitted model versus experimental activity versus the predicted activity. So these are the various stages that we follow in QSAR. Let us discuss what at different levels: 1D, 2D, and 3D. 1D is just a molecular formula; it gives only the atom counts. 2D will give information about the connectivity and also the functional groups. 3D will give the information about spatial arrangement and conformations. So these structure contain all the information required for a property. So this is the first stage of the QSAR input. Then the molecular descriptors. These are the numerical representation of that molecules. The molecular structures are converted into quantitative descriptors. Common descriptors like constitutional number of atoms and bonds and rings, electronic descriptors like charge distribution, dipole moment. Geometrical descriptor means molecular size, shape, volume. Hydrophobic and lyophilicity, log P. So these are the hydrophobic constant. And solubility related is hydrogen bond, donors and acceptors. Steric related descriptors, the bulkiness, van der Waals volume, etc. Quantum mechanical descriptors like HOMO, LUMO, gap, electronegativity, etc. Then the topological descriptor like Wiener, Zagreb, and Plotnum. So these descriptors acts as independent variables D1, D2, etc. in QSAR. So then the third stage of QSAR is data pre-processing. So raw descriptors data is refined before modeling. So that is by normalization or standardization, removes the scale bias. Then the feature selection removes redundant or irrelevant descriptors. Then outlier detection improves the model reliability. So this data pre-processing ensures statistical validity of QSAR model. So then the fourth one, the multivariate analysis or model building. So it's mathematical relationship established between the descriptors and the biological activity. So in common QSAR model methods like multiple linear regression method, principal component analysis PCA, then partial least square PLS, then self-organizing maps SOP, and neural networks ANN, then support vector machine. So these are the various QSAR modeling methods are being adapted. For general QSAR equation, the activity is equal to, I have already explained, C0 is equal to C1, D1 plus C2, D2, etc. So then the fifth stage is the statistical evaluation of the model. This model quality and the predictability are assessed using R. R is called correlation coefficient, and R square is the goodness of fit, and Q square is the predictive power, so cross validation. MS is the mean squared error. RMS is the root mean squared error. It ensures the model is not overfitted. So then the sixth stage, that is a prediction and validation. QSAR model predicts the activity of a new or unseen molecules. Predicted activity is compared with the experimental values. So good QSAR model shows I R square, that is goodness of the fit, and I Q square, predictive power. So high goodness of the fit and high R square predicts then that QSAR model is the best one. And low RMSE, low root mean square error. So linear versus experimental versus predicted plot explains how good that QSAR model. So overall, the QSAR converts the molecular structures into numerical descriptors and correlates them statistically with biological activity to predict the behavior of new molecules. Then another concept in QSAR QSPR is geometry optimization. Geometry optimization is the process of finding the most stable molecular structure. It's achieved by minimizing the total potential energy of a molecule. Atomic positions are adjusted until forces on all atoms become zero. So corresponds to a minimum and a potential energy surface, that is PES. Why is this geometry optimization is needed for this QSAR and QSPR modeling? So experimental geometries may not be available. So therefore it ensures the realistic bond length and bond angles, physically meaningful molecular structures. So this geometry optimization is required before energy calculation, vibration analysis, descriptor calculation, and QSAR and QSPR studies. So what are the methods used for this geometry optimization? So there are various methods. The first one is the molecular mechanics uses force fields fast. It is fast suitable for large molecules. And semi-empirical methods, it balances between the accuracy and speed. And the third one is ab initio or DFT methods. So DFT methods are high accuracy and computationally little bit expensive. So this one. So what are the optimization criteria? So energy change below a threshold, forces on atoms approach zero, atomic displacements become minimal. So the significance of geometry optimization in computational chemistry is that it provides the theoretical geometries free from experimental errors. It ensures the consistent structures for all molecules in data sets. It's essential for reliable descriptor calculation, accurate QSAR and QSPR prediction. So overall geometry optimization finds the lowest energy, most stable molecular structure required for accurate computational predictions. You can see this is the graphical representation of this geometry optimization. So the y-axis is the energy and the x-axis is the conformation. It's a three-dimensional arrangement of a molecule. So during geometry optimization, initially there will be a high energy to start with. Then after changing from one conformation to another conformation, you can see that there is change in the potential energy. So this is the local minimum. Then again, this is the global minimum. So this is the maximum. This is the most stable structure corresponding to this configuration. So this provides the details of bond length, bond angle, steric index, molecular interactions. Obtain the various conformations, geometry of the molecule. Computed Gibbs free energy values are also obtained from this. The lowest is chosen as a standard, as a stabilized, the most stabilized conformation. So the conformation corresponding to this energy, so that structure is actually most stabilized structure. So with this, I'm just summarizing the entire unit, that is computational chemistry. So the summary, the molecular modeling to the property prediction. So molecular modeling uses computational methods to study the molecular structure and behavior. It offers high cost efficiency, time saving, and the predictive capability compared to real-time experiments. The molecular properties depend on bonding and non-bonding interactions. These things we have discussed in the first recording of this, the part one. Then the second one, the molecular topology, molecules are represented as graphs, like atoms, vertices, bands as edges. And the structural information captured using topological matrices like vertex adjacency matrix, edge adjacency matrix, and distance adjacency matrix. So this is the first one. This is the first recording out of one. And the second part is covered in the second recording out of four. And next we have discussed about in my previous recording, that is third by four, topological indices. So these are the numerical descriptors derived from molecular graphs and from the matrix representation. We have discussed about the geographic indices 1 and 2. This is related to degree-based connectivity. And the second one, the Wiener index, W, it is based on the distances between the atoms, the molecular distances. Okay. Then the plot number P and F of G is a bond-to-bond adjacency and branching. So this we have discussed in the third part of this unit. And then in this video, I have just covered the last part, that is the QSAR and QSPR applications. QSPR predicts the physicochemical properties. QSAR predicts the biological activity. So it uses topological and molecular descriptors to build predictive equations. So it enables in silico screening, reduces experiments, and guides rational design of new molecule. This is so. With this, I'll be completing the recording of this entire unit 5 on computational chemistry. So hope you guys understood. The overall conclusion for this entire unit is we started from the molecular structure, the molecular interactions, the molecular structures, then to matrix representations, to numerical descriptors, that is topological indices. Then from that to mathematical model, that is QSAR and QSPR model. From that, we have understood how the property and activity of a new molecule can be predicted. Thank you. Hope you understood all the 3 videos. If you have any doubts or comments, you can comment. Okay. Thank you all.